Okay, this is the last one in this sequence. We're continuing with decision analysis. Whoops, I didn't want to do that. Hold on here. Let's see. There we go. So I want to talk about dynamic programming because this is a really powerful tool. And as I said at the beginning, I really just want to expose you to the algorithm. You will not be doing any programming. This is something that is used in computer science quite often to solve problems using algorithms. It's a really great tool. I just want to expose you to this idea so you'll be familiar with it. And it can be used for scoping out projects, which is the focus of our course, right? So the idea is that we can find optimal solutions, not the optimal solution necessarily, but optimal solutions nevertheless, using this state space search technique, the trees. But this clips the trees, and I'll show you how that works in a minute. It doesn't. You don't have to look at the whole set of decisions, only the ones that give you the most return. Um, this approach is great when linear programming and other techniques uh, don't fit. So you don't have a convex feasible solution space. You have nonlinear relationships. That kind of thing, right? So I'm gonna step you through this. Oh, look at that! I just said that. Okay. So obviously, right? Obviously, many problems are not amenable to calculus solutions. They're not amenable to linear programming. So the idea here is, let me give you an example of state space search without using dynamic programming. So let's say I want to travel from San Francisco to Boston. Right? What are my choices? So let's say it takes 10 days. I'm going to take 10 days, and at the end of every day, simplistically, I have 10 choices to make, 10 different routes I can take. That means if I want to use just raw state space search and represent all of those choices on a decision tree, I would need to include 10 to the 10th choices. Not feasible, right? Not feasible at all. So I'm going to show you, I'll show you this in a little bit here, but I'll show you that kind of that same thing on a smaller scale that's used for finding the least time path, or the best time path, I should say, through a network, travel network. So here's San Francisco, and I've got 10 choices. I only pictured 5 because I didn't want to have to draw the extra 5 arrows, but you get the idea. So at the end of day 1, I'm in Las Vegas, and then I've got 10 more, and then I'm in Chicago, and I've got 10 more, and so on until I reach Boston. Too many choices, and really impractical to represent this. So this is a picture of a simple network with only 8 routes, right? 4 horizontally, 4 vertically. And if to get from A to B, if I were to represent this in a regular decision tree from A to B, I'd have to look at 40 different paths just for this simple little network. So this is perfect for dynamic programming. So I'm going to show you how to make it through a network of street segments. So we begin at the origin node, and the idea is to travel to all nodes that are connected to that first node, right? And those nodes are considered to be open. And then I'm going to record the cumulative travel time to each node from the origin node and eliminate the paths that don't give me the best time, the lowest time. And I'll close the previous node, choose the open node closest in time, and then just keep going, repeat. So I have an example here I'll show you. Here's a simple network. I'm going to start at node 1, and I want to go find the minimum time path to node 8. Obviously, it'd be pretty easy to just find it, using just looking at the picture because it's so simple. But I want to show you the algorithm using this simple network. So the idea is I'll travel from node 1, I'll open node 1, and travel to all of the nodes that are connected to it, 2 and 5. The travel times are associated with each link are written on the link. Okay? So the cumulative time from 1 to 2 is 1, and from 1 to 5 is 2. And I can close that off. So now I'm going to choose node 2 because that's the closest. And I'll travel to all open nodes. And the cumulative time, this is called the return function. And the return is 3 plus 1. It's 4, and this one is 4 plus 1 is 5. Okay, now this one is the lowest one, so I'll travel from here to 6, close that off, and see now I have a decision to make. I've been able to travel to this node from 2 different paths, and I'm going to choose the one that gives me the lowest travel time. That's the highest return on my investment, if you will. So now I've got 2 4s. I can choose either one I want. I'll choose this one. I'll go from 6 to 7. That's 3 plus 4 is 7 minutes. And now travel from 3. And those are 10 and 6, respectively. And see, now this way, I can get here in 6 minutes. So I'm going to eliminate these choices. And then one more. I'm going to go from 7 to 8. And it'll take me 2 minutes, so that's 8. And then 8 to 4. And it eliminates that. So now this shows me simply the minimum time paths from node 1. There we are. That's using a very simple example of dynamic programming. It's basically setting up a network, and then it's really a tree, a decision tree, and then only looking at the nodes that give you the best return. So I can set this standard problem up with stages, and actually, well, let me explain this, and I'll go to the example in the next video. So I'm going to set this up in a similar way to the travel network, but this is more general. Basically, I'm going to set up a grid with columns and rows, and I'll define 2 terms, costs and benefits. And that can apply to just about any of the problems. So the costs and the benefits. And one other, of course, the choices. So I have choices, costs, and benefits. And the choices really are kind of and then I have to keep track of the state of the problem. Where am I, and what path have I taken? So the returns on the choices, the benefits, are really the travel times on the links accumulated at each node, right? So how can I organize this in such a way that it looks like a network, right? A simple grid. And what formula will I use to optimize? So it's either the travel time function or some return on investment. The benefits. Are there any constraints? And then, what's the solution? So I'm going to show you another example, but I've gone through another 10 minutes. So I'm going to start this example in the next video.